thank you very much for giving me the opportunity here to say a few words before the real thing starts. So it seems now as if I have reached the age that people are asking you just for, yeah, could you give a few greetings or motivation, and the real thing we are doing then, which is a pity. But of course, I thought, okay, so what should I tell you? The point is, of course, you know me, I'm a computer scientist like Jörg, and for a few years ago, for the first times, we met people from the material science domain. Since we are computer scientists, of course, we are dealing a lot with artificial intelligence, so don't be surprised that there might be a few pictures from Stable Diffusion here, which I asked to show us material scientists, of course, historical photographs of material scientists. The interesting thing now, recently, of course, you might have heard of the advent of large language models. And of course, also this news has reached the realm of material science. And from several colleagues, I was addressed and told, yeah, why do we need this fuss with the ontologies anymore? We have these large language models. And I did some experiments, of course, small kind preliminary experiments and stuff like that. And it seems as if these language models do have really a stable, solid knowledge about material science. So why should we then represent that kind of knowledge with ontologies? Why do we do all the fuss? Yeah, of course, that was a very good question. So I thought to myself, yeah, that might be a topic that I might address here in my few first words. And so do we still need ontologies in material science? And of course, we computer scientists also are using large language models. So I thought to myself, okay, let's ask this question to ChatGPT. So I was asking, do material science still need ontologies now that there are large language models such as ChatGPT? And I mean, despite the fact that, of course, here it's about the importance of ChatGPT itself, it answered, yes, material science still needs ontologies and so on. If you ask looking deeper into the answer, then you will find why they need ontologies. And of course, they are critical, as it says, for enabling interoperability. And of course, also data sharing, data integration, and also automated reasoning and decision making. These are things, of course, where ontologies really then can, in a structured way, in a logical way, support material sciences beyond the scope of which a large language model might be able to. So if we think back here in the ontology playground, we dealt for several, or let's say for a long time, with the process or the problem of how to cook an egg. So here you see two material scientists dealing exactly with that question. And of course, I was asking also ChatGPT, so help us now how to boil an egg. And of course, please give the answer in terms of an ontology. And you see what it did. So we get interesting combination of an object, which is an egg. We have to model an action, which is boiling. We have tools like a pot, stove, and water, and we have ingredients. And then there come the steps. Of course, this is kind of an ontology expressed simply in natural language. So I wasn't completely, let's say, satisfied with that kind of answer. So I was then asking, okay, maybe ontology is also not the right tool for cooking an egg. So do you need an ontology to cook an egg? Obviously, no. So we, of course, assumed that it would be that way. However, as it says, ontologies can provide a structured way of representing the knowledge and information related to the process of boiling an egg. And of course, then I thought to myself, yeah, that holds for general use case. So now let's ask, so what's the material science perspective there? So does this answer also holds for material science? And yep, it says yes. So in this context, an ontology can be useful for representing chemical and physical properties of the egg and the water and so on and so on. And of course, we also saw for ourselves, and it was proven that, of course, the process of boiling an egg served as a really great template for us to think of how to model processes, which are, of course, the main subject here in material science, what we want to represent. Of course, many of you already asked right in the beginning, so there is now PMDco, so also the subject of today's presentations. But of course, there are other or further material science ontologies, like, for example, MO. And the question, of course, that comes up now, isn't MO enough for material science? And of course, ChatGPT shows off a bit because it tells us, yeah, of course, I know what MO is and so on. But it says there might be the need for additional general ontologies to represent knowledge in the field, as we found out. So there is a reason why we did PMDco, and it's of course not simply to represent different knowledge. It was also the purpose we had in mind, like things, for example, query efficiency, making things not too complicated, making the barrier for using it in the realm of material science rather low and stuff like that. So these were our intentions when we were designing PMDco. In the end, I want to close here with more modern material scientists, as you see them here now in a colorful picture. And ChatGPT sums up everything quite nicely by saying simply, therefore, while large language models such as ChatGPT can be useful for natural language processing tasks related to material science ontologies, remain the critical tool for organizing and representing information in a machine-readable and interoperable way. And by that, I end my talk, and I want to hand it over to the main subject here of the day. Thank you very much for your attention.
Well, thank you. I think the use of AI this is a trend. So we are very on trend using Stable Diffusion and ChatGPT, of course. And I like how self-critical some answers can be of the system itself. And we should also, and this is a good, I think, segue into the next presentation, be critical about what we're doing here. I think this playground is the place to voice also critical opinions and concerns, and we find solutions together. That's why we play around with not only problems, but in the end also cool solutions that already exist. So there's another puzzle piece to the solution set. The presenters for this PMDco version 2.0 release will be Bernd Bayerlein and Jörg Waitelonis. Jörg will go through some of the very detailed examples that we already have and show a subset of that, but you can see how this works. It's pretty similar to the concept board design that we do here live sometimes. And Bernd Bayerlein will be the lead of the main presentation.
Yes, exactly.
And there we go.
I think you can already see the slides and you hear me, hopefully. Thanks, Harald. It was a really, really interesting introduction. Really liked it. Now let's go a little bit more into the detail to some decisions we made for the platform MaterialDigital core ontology. In short, it's PMDco version 2.0.0. And I also have a motivational slide here, and this is actually part of a publication. It will be public in a couple of weeks. It's already reviewed, and we're just waiting for, I think it's the June edition of Advanced Intelligent Systems. And what this figure a little bit summarizes is the condensed product of studying many publications that have a semantic web technology as content, but also try to advance the material science and engineering field. And so on the left side, this is an example on semiconductor optimization. It's just an example. It really doesn't cover everything there, but what you would have in this optimization is you would have several experiments, processes, or some manufacturing steps, and all these part disciplines more or less have their own or produce their own metadata and data, and they all come in heterogeneous formats, and it's very unstructured data what you have in the end. And there are domain experts shown here that maybe studied even some disciplines here, and they can really be able with some advice to formulate the critical concepts that would be then kind of finalized more or less in an application ontology. And this application ontology, they can be kind of interconnected with an upper ontology. This would be here this black construct. And this could be in the end, maybe it could be EMO, but it could also be like the PMDco. And by fueling this ontologies, or you apply these ontologies, and map data to it, you would then be able to store these resulting triples in a so-called triple store. And based on this triple store, you can then, by applying another thing, which is called Sparkle queries, you can flexibly retrieve information here. You would be able, depending on your ontological representation, maybe also to gain some new knowledge. Yeah, but this depends strongly on how you model stuff. And you would, by providing these highly structured data set, you would support also machine learning models. Yeah, and in the end, what is kind of a necessity also in our domain is to say, okay, this peak here maybe is the result of some decisions made here. And this is what is shown here with this data provenance. Provenance is just a part of metadata, but this would help to make these experiments and the resulting data reproducible. And if something is reproducible, we would be able to reuse it, the data. And I think this is a big goal. But this here looks quite simple. Yeah, there's many technological steps here that that need an understanding here. And this is really a problem with applying this technology, that these entry levels are still super high. Yeah, and therefore I come here to the slide with the MSE community requirements. Already said we have at starting points, we have a literature survey also based on this publication here, and also we also studied other material science ontologies. Then we had the ontology playground now for a couple of years, where we heard we heard the partner projects of MaterialDigital 1. We had many discussions on modeling, even with starting how to model it, how to develop ontologies. And we asked at some point, please think about what should your ontology answer. And then they modeled, summarized, or we have a repo where the competency questions of you are kind of available. Yeah, and from these starting points, these requirements can be more or less derived. Yeah, and this is what I already mentioned. User friendliness and low entry levels is really, really important. Yeah, then we want to have processes and data reproducible, and we want to be able to represent object processes and processing nodes interdependencies. Yeah, so in the end, maybe I want to know, okay, I have reached this performance of my material. Maybe I need to optimize some processes prior to this result, and therefore these interdependencies are very important. And in the end, I want to be able to, in an easy way, also retrieve my information. And this are all the requirements for our, I would say, first decision we took here, that this high-level layout of the PMD core is aligned with the provenance ontology provided by the W3C. It's a slim, basic, and stable ontology. It comes with a user-friendly documentation, and especially it was developed for representing and exchanging provenance information of digital workflows. And therefore, it's actually an ideal basis for these reoccurring patterns in support of material science and engineering process reproducibility. Other design and purpose features are listed in this slide. It's an ontology for materials science and engineering domain. And we want to provide the mid-level classes that the partner projects, so you are and others maybe also, we want to reach the whole domain, not only the ones that are funded by the BMBF, that they are able to connect to their domain-specific application ontologies to some more abstract classes that are given in the PMDco. And this could be or will be a common framework for describing and organizing metadata and data. Already we reuse ontologies such as the QUDT and the CHEBI, and this high-level layout already mentioned. And when we look a little bit deeper how then these essential classes, structure, and relations look like, this is a schematic that is easily to understand. So on the more or less basis, we have the PMD process. Processes can always have next processes, so you can really model a whole process chain. There's also other properties. For instance, you can have subordinate processes and also parallel process and so on and so forth. You would have an input or output of a process, which is an object. Object could be composed of other objects, and these processes are executed by, or processing nodes execute processes, and these processing nodes can also be built up of others. And from all these bottom essential classes, they point to the other essential class, which are the value objects. And value objects are, this is our metadata, our data. They are found in the value objects, and you can even classify here if it's metadata, if it's primary data, or even secondary data, which would be the case if you, for instance, have as a primary data an area you measured and you calculate a radius. Then would be your radius as secondary data, and you would have also the possibility to classify it as measurement or set point, and set point is something that is really important also in material science and engineering. Here, these objects, for instance, can be real or digital. So my test specimen would be a real object, and if I break my test specimen and would look with a scanning electron microscope on the fracture surface to classify the fracture mode, then I would have an image, and this image would be then digital. Processes are actually activities such as experiments, methods, workflows, and these processing nodes I mentioned already are machines, equipment, tools, accessories. And with modeling process chains, you would maybe end up in a crowded slide like here. So it's very simplified, but it's already kind of too much for one slide. So I will just quickly go over this before I hand over to Jörg, who will then go deeper in some of these modeling cases on our Miro board, where the documentation of the PMDco can be found. So here in this T box, in terminological box, we would have here this processing node, as I explained already, process, object, value object, and here also value scope, which has the subclasses measurement and set point. And in this first process line here, we would have, for instance, a sheet, a metal sheet or a steel sheet. This is heat treated here by an oven. This executes this process. As an input would have a steel sheet, and as an output would have a heat-treated steel sheet. And characteristic for this first process, and this is just one characteristic of this process, and this would be here the measurement of a temperature curve. You're right, maybe when you think, but sorry, there must be also a set point. You're right. Each heat treatment has its specific temperature, and this would be then the set point for this. Then you see the next process would be here to manufacture a test piece. So you would have some thing that maybe cuts out the test piece. And as an input, we would have the heat-treated sheet. This would be kind of cut. And there is a characteristic for this very simplified process. We would have here now a set point, because according to a specific standard, for instance, for the tensile test, you would have a specific test piece dimension. And if you would not reach this dimension, then this whole procedure, this testing procedure, is not guilty. Okay, and so forth. I don't want to go into so much details here. I think now it's a good time to jump to the Miro board for further explanations by Jörg Waitelonis, and I stop sharing here for now.
Thank you very much, Bernd. I will now start the sharing of the Miro board. So we set up a Miro board with a lot of examples how we suggest to use the PMDco ontology. And I will go through some of them now. Bernd already explained a lot. However, I will quickly introduce the basic concepts. And we already heard that there are three main things, which are the processes, which might be analysis processes, simulation processes, assembly processes, and so on. There are also processing nodes, which might be furnaces or measuring devices. There might be objects, like pieces of material or images or something like that. And they are connected, so processes might be executed by processing nodes, and processes or objects might be participants of processes. And we've already heard that processes might have successors like which are modeled through the property of next process. And processes are executed by processing nodes. Here, for example, there is a measuring process defined, which is executed by a node, which might be a caliper, which is a measuring device, which is a processing node. So you can see here some sort of a taxonomy of different devices, which we have, where we have provided a lot of examples in the ontology tree. Yeah, processes can also be associated with operators. The Prof ontology was associated with property, and operators may act on behalf of a laboratory. Also here we reuse just the properties from the Prof ontology. And of course, processing nodes might act on behalf of an operator. Okay, so these are the basic concepts. Now let's have a deeper look on the process itself. I mean, so processes can have inputs. Inputs are actually objects, which might be images or samples or test pieces. And of course, this also holds for the output properties. So processes can also output objects. There's also a way to split up processes in sub-processes. Here we've introduced a property which is called subordinate process. So for example, if a mounting process incorporates two steps, then we can model this through the subordinate process property. Process can also exist in parallel. This is easily modeled just through the next process property, which can be chained in different ways. Like here, we have two parallel processes, 2 and 3 are executed in parallel. This might not necessitates that this is also a timely parallelism. I mean, from Prof also also a start and an end time of a process might be provided, and but this you can do this, but you don't have to. Processing nodes. Reintroduced the value object. I will go in detail on this later. Processing nodes can, for example, be identified by metadata, or this can be described by metadata. Here, for example, we have a furnace, which has a component, which is a slide, which is sort of part of the furnace. And it is described by a characteristic, which is a value object, and in that case, a serial number, for example. So if the oven you use or the furnace you use has a certain serial number, then you can specify this through providing a value object or creating an instance of a serial number, which then has a value, and the value then actually contains the number in terms of numbers and letters, like a string, value. Processing nodes can have additional metadata. Now it's getting a bit more complex. Just a second, yes. Here we have an example where we have a furnace, which is actually a vacuum furnace. But here you can see that this in this class of the vacuum furnace is not stemming from the PMD core ontology. Here we have provided an example where some application ontology introduces a new class, which is a subclass of the PMD furnace class. And this is how you might introduce your own concepts to the entire model. And this furnace has a characteristic, which is, for example, a manufacturer, which is also an organization, which is also an agent. And this manufacturer, for example, might to the actual it might have a link into your own ontology, which at the end might represent the brand or something like that. Coming back to the furnace here in this example has different characteristics. It might be a node model or a node series or a node name and the node serial number. So what it actually shows here is that you can use multiple of these characteristics to describe the furnace. And all this information is set to be a metadata, which is a subclass of data scope. I will introduce this on one of the next slides. Okay. So objects. Objects are sort of real engineered materials. It is something you might touch, for example. And here we have an example where we have an instance of a microscopy process, an electron microscopy process, and the input is a specimen, and the specimen is a subclass of sample, which is a subclass of engineered material. There are, of course, other kinds of engineered material, like a blank or a base material. This is especially interesting when it comes to the modeling of mass fractions. Objects might also be digital items, like, for example, images. Here again, the microscopy process. The input is the specimen, and the output is an image. Both specimen as well as image are at the end objects. Objects can be composed of other objects. Here, again, the egg cooking example, and also here we are introducing some classes from an application ontology. There is the separation process here on the left side, which is subclass of a baking process, which is subclass of a process, and there's a subclass of a Prof activity. And the input of the separation process is an egg. And the egg itself might be composed of the egg white and the egg yolk. And the separation process then creates the output, which is the yolk and the egg white, and the input is the egg. So this is how a object composition might be modeled. Yeah, I think I already introduced the identifiers. So yeah, I will skip this slide. The next are the value objects. Bernd already introduced the value objects. The value objects for us are the value object is defined as something which represents a specific value. This might be a length or a area or a force and so on. And there are many subclasses in the ontology below the value object. And these subclasses specify the kinds of values. And these values actually are maybe numerical, textual, or complex data structures. And we use the characteristic property to associate them to the actual items we are going to describe. And value objects might also refer to units, and and they can be used together with processes, objects, processing nodes, and projects. Here's one example. So there is a measuring process, and the measuring process has a characteristic which is a length, for example. And now let's include the value and the unit for this length. Here we have the value object, which is a length, and we can use the PMD value property to refer to the actual number, and we can use the PMD unit value to refer to a unit. And here in that case, we propose to use the QUDT vocabulary or ontology, which provides a lot of different kinds of units and also more information. So in that case, yeah, we suggest to use it. We also introduced some more units like pixel unit and pixel per nanometer, which are defined as individuals in the PMDco, and we did this because they are not present in the QUDT vocabulary. So here we see that a value is referring to a scalar value, so just a single number, but there are also methods to refer to lists. And here we have we propose different solutions. One is to use RDF containers like RDF list or RDF bag, sequence, and alt. And this is how it might look. So we have the value object, which is a length, but now we have a list of lengths, and it is, instead of using the PMD value, we now use the PMD resource property, which can refer to arbitrary instances of for example, the beginning of a sequence. And we can also use the unit to express that the sequence items are have the respective unit. We also provide we make a suggestion how to also refer to table or tabular data. Here we suggest to use the CSVW vocabulary, which is also which is defined also through the through the W3C. And this might look like the following. Again, we have the value object which is a length. And now again, we use the property PMD resource, which now points to a CSVW table, which itself has 2 rows. And each row can then again be described through a identifier and the actual value and also a unit. Okay, there's also a way or a method where you can use the web annotation ontology. This is especially interesting if you refer to specific values which are located in, for example, documents or PDF documents. And this might look like the following. We have the value object, which might be a length. The value object has a value and a unit. And to express that this value stems from a certain file, which might be a PDF, like here, for example, an online version of a PDF at example.org some.pdf. And here we use the web annotation model, which says that there is an annotation, and the annotation always has a body and a target. And the body is our value object. So this is the thing we annotate with the target. The target is the document, which has so the target has a source, which then points to the actual URI of the document. And we can also provide a selector, here in that case a text position selector, which says at which, for example, letter or word, depends on the concrete definition, then this value occurs in the document. This might also be a page or so. There are different kinds of position selectors described in the web annotation model. This also works with HTML documents or also JSON documents or other kinds of digitals. Okay, so this was the value objects. Yeah, and then Bernd also mentioned the different kinds of data scopes and value scopes. So we had the example where here the length, we used we have the measuring process, and it is described by a length, and the length maybe has a value, which is not shown here, but we also would like to express if this length is something which was measured by a process, and if so, then we can also make this instance of the value object an instance of measurement, which we see here. So here we have again the measuring process, which has a length, and the length has a value and a unit. And to express that this value was measured and not used as a set point, we can make this instance also a subclass of measurement, which is a value scope. So there are two subclasses in value scope. The one is the measurement and the other one is the set point. So if you have a process which needs some sort of a preset as input, then you can model this with the value scope of set point. Set points, for example, or also yeah, set points might be reused. Here, an example with a mechanical testing process, which there are three processes which are mechanical testing processes, and they are yeah, there are some subsequent processes, and all have the same preset, which is a preload with a certain value, and this preset is reused, or the set point is reused because all three processes point to the same instance of the preload. Yes, this was the value scope, and we also have a similar principle to specify if a value object is considered to be primary data or secondary data or metadata. Here, for example, the length, which is measured as primary data, then also is just an instance of this class. And if you then later on use this primary data value to calculate some more data, then you can define this as a secondary data. If you have names or IDs, then you can define it as metadata. Okay, how to refer to data sets and external files. So,
Jörg, just to interject here just for a second, you're going through the whole documentation right now. I think we have like 15 minutes left.
Almost done.
And I have to play so-called time cop here. Okay, I'm just saying out loud. Okay, go ahead. Thank you.
I just want to go. Yeah, I will speed up. How to refer to data sets and external files. Here we suggest to use the DCAT catalog. Yeah, to vocabulary, and I will make it quick. We also provide some examples to use again the CSVW vocabulary, where you can describe the header of a table, but the actual information of the data stays or remains in the actual file somewhere on your hard drive or in the web. And to refer to image and media data, we also, you can use this again similarly to the other examples where you, specify images, for example, as output and input. And what else do we have? Yeah, I think, okay. I will skip the rest. You see there is much more, and it was quite an effort to make all these examples, but we think that providing all these examples makes it easier to get an idea how to use all these the ontology, basically. Okay, so I will give it back to Bernd. Thank you very much so far.
Exactly. Thank you, Jörg, also for this, going through almost the full documentation, but actually it's super needed, yeah? I mean, you want to use something and you have to understand how to use it, yeah? And it's only 3 slides left before we go to the discussions. So first of all, here's the where you can find actually the PMDco. You can either use this QR code or you type this in. Actually, everything related to MaterialDigital, which is public, is in this GitHub here, and in /core ontology, you find exactly this screen, which is a screenshot from this. So this will be kind of dynamic because it will at some point have also an extensive README document, and maybe this Miro board documentation will change its shape somehow, but as there are always new questions how to model this and that, I think this documentation is growing. The same holds for the PMD application ontology. So there's also in the GitHub MaterialDigital, you can find this. There's already the heat treatment ontology, and there's the tensile test ontology I was referring to at some points of the previous presentation. And it would be nice at some point if we would collect all application ontologies that are built on the PMDco in this repository, and also to make it reusable, an application ontology. I mean, it would be great to have a documentation which Markus Schilling already provided here for the tensile test ontology as main developer. And the last slide is, this is, we could have a summary or a conclusion, but there, in this case of ontology development, there's always room for improvement. And this is also our ending slide. And the first question maybe is how to manage new features, changes, make suggestions. First of all, I showed you the place where you can put in issues in this GitHub. We are actually now in this ontology playground, which is meant to be the future, the past, and will be the future forum for discussions and even decisions. And we want to establish a review process also with your contribution. You see here the community interaction is actually the tip of this construct. So what are to-dos? In not a specific order. So at some point we have to modularize, to increase also reuse. Maintenance of descriptions and labels is very important. All these new classes, the extending taxonomy, which comes with the PMDAO development, which showed Jörg already in this documentation, this has to be done. Also, mappings to other ontologies are crucial. And of course, for these application ontologies, we need a shared namespace.